Okay, well let's take a look at this next section. This is section 5.5. It's on applications of vectors. And in order to do this section, let's take a quick look at just a couple of things that we need to remember about parallelograms. So I've got a parallelogram over here, and then we want to think about what do we remember about the opposite sides, the opposite angles, the consecutive angles, and the alternate interior angles of a diagonal. So I'll draw a diagonal in just a second, but let's talk about opposite sides. If we look at opposite sides of a parallelogram, we know that they are congruent. Okay, congruent. So they have the same length, same measurement. And if we look at opposite angles, so if I were to look at this angle right here, and this angle right here, and this angle right here, and that angle right there, we know that opposite angles are also congruent. And then if we look at consecutive angles, so when we say consecutive angles, we're like saying these two in a row, and those two in a row, and those two in a row. And if you'll remember, these two add up to be 180 degrees. In other words, they're supplementary. Supplementary. All right. And then in order to do this next one, I'm going to need to draw in a diagonal. So let me go ahead and do that. I'm going to draw this diagonal in right here. So from that corner to that corner. And we're talking alternate interior angles of a diagonal. So I'm talking, I've got this parallel side on the top and this parallel side on the top. I've got this line cutting across the two of them. We call that a transversal. This angle and this angle, those are congruent. So I'd have that angle is congruent with that angle, and that angle is congruent with that angle. Okay, so alternate interior angles of a diagonal are congruent. And of course, the two of these add up to be that angle in that corner there. So the reason we study vectors is because if we have something that's moving or forces that are interacting, we've got two forces pushing on the same object or something like that, that type of motion and that type of problem can get very complicated. And if we use vectors to break that motion into its components, it can make it a lot easier to solve, and we can figure out some fairly complicated problems. So we're going to take a look at this first problem right here. So it says, two draft horses are pulling on a tree stump with forces of 250 pounds and 280 pounds as shown. If the angle between the forces is 60 degrees, then what is the magnitude of the resultant force? In other words, how hard are they pulling on there? Okay, and what is the angle between the resultant force and the 280-pound force? So we could look at this and we say, well, this one's pulling with 280 pounds and that one with 250 pounds. Well, the resultant ought to be, well, let's just add the two of those together and get 530 pounds. Well, it doesn't quite work that way because they're not pulling in exactly the same direction. And maybe this farmer's got a good reason for putting them that way. Maybe they don't get along very well, so he's got to keep them 60 degrees apart or something like that. But regardless, here's the situation that we've got, and we want to find out two things. What is the magnitude of the resultant force, and what is the angle between the resultant and the 280-pound force? So one way that we can solve this is we can go through and we can say, well, look, let's just draw a picture here. So let's remove the horses from this. So let's say we have our 250-pound force here. We've got our 280-pound force here. We'll make that one a little bit longer. So this is 280 and this is 250. And what we're after is the resultant. Well, we're basically just adding two vectors together. So I could make a copy of this one and put it over here. We could use the parallelogram method, and a copy of this one and put it over here. And the resultant would be this right here. Remember, it's from the tail of both of them to the tip of both of them. That right there is R. And then we could label this one over here. This side right here would be 250. And then we'd have a triangle that we could solve and figure out what the length of that side was. So we've got to think about this for just a second. If this is 250 and that's 280, I've got to have an angle on there in order to figure this out. Well, if this was 60 degrees, if this whole thing here was 60 degrees, I can figure out what this one is because I've got consecutive angles. Consecutive angles are supplementary, so that means this is 120. So here's the triangle that we're working with all together. So let me change colors and I'll just draw this. There's our diagonal, our resultant. There's our 250-pound force and there's our 280-pound force. So this is 280, this is 250. This is 120 degrees, and this right here is our resultant. Okay, so this is what we want right there. Well, this is a law of cosines problem. So we would start off with the side. So this would be r squared equals, this is going to be 280 squared plus 250 squared minus 2 times those two sides. So 280, 250, and then the cosine of the angle between them. So that's going to be the cosine of 120 degrees. So that means r is just going to be the square root of this. So I'll just put a big square root on there. And let's figure out what this is right here. So I'll turn on my calculator, clear this stuff off. Always want to check the mode. Okay, in this case I need to be in degree mode. Okay, so we're in good shape there. I'll hit quit, and then I'm going to type this in. Big square root 280 squared plus 250 squared minus 2 times 280 times 250, and then times the cosine of 120 degrees. Close the parentheses, close them again. Always a good idea just to double check and make sure we've got that typed in there correctly. I'm going to hit enter, and I get 459.23. So that means r is equal to 459.23. And we should put some units on that. That's going to be pounds. Okay? So it's not the two of them added together, but it's definitely more than either horse could pull by themselves. So we've got that right there. Now, the other thing it asked for, after the magnitude of the resultant force, we've got that, is the angle between the resultant and the 280-pound force. So here's the 280-pound force. So what they want is, they want this right here. They want that angle. And it's important to make sure you read the question and know which force they want us to find the angle with. We could find this one up here too if we needed to, but we'll talk about that in just a second. So let's think about how we would do that. Well, if I know that this now is 459.23, I've got all three sides in one of the angles, so I could do this. If I want to find alpha right here, I could say that the sine of alpha over, I've got that corresponding side there, 250, equals the sine of 120 over 459.29. And I've still got that number stored in my calculator, so let's see what we do here. We'd multiply both sides by 250 and then take the sine inverse. So alpha would be equal to sine inverse of 250 sine 120 over 459.2, whoops, that was a 2323. And again, I'll have the calculator figure this out for us. So I'm going to do sine inverse, and remember, this is going to give it to us in degrees. So this would be 250 sine 120 divided by that last answer there. So I could type in the 459.23, or I'm just going to grab that last answer, close the parentheses, and it tells me that it's 28.12. So we'll go to the nearest tenth now that we're at a point where we can round. So we've got 28.1 degrees. So there are the two answers to this problem. Now, this should make a little bit of sense, because if this horse is pulling harder, this resultant is going to come more in line with it right there. So if we've got 60 degrees between the two of them, we would expect the resultant to be closer to the larger of the two forces. If they happen to both be the same, it would be right down the middle. It would probably be 30 degrees for each one of them. Okay, so we've got 459.23 pounds for the magnitude and 28.1 degrees for the angle between the resultant and the 280-pound force. So I told you we'd come back to this. What if we wanted the angle between the 250-pound force and the resultant? Well, that's pretty easy, because if you know the whole thing is 60 and you know one of them is 28.1, we just do 60 degrees minus 28.1, and we'd have the answer for that one. It's a little bit further away from that, so that would be what? 31.9 degrees. So a little further away from the 250-pound force because it wasn't pulling as hard. So that's a really interesting application of vectors, and in this case, an application of the law of cosines. But another way to do this is to put this in component form. And it's not like you have to do this on every single problem, but I would advise you to do some of these in component form. So let's talk about that first horse. Let's talk about that 250-pound or the 280-pound force. He's pulling directly this way. So let's think about what that would look like. If this is 280 pounds, the angle from standard position, you'll remember, that would have to be 0. So we could call this horse 1, and we could say horse 1 is putting all of its effort in the positive x direction, if you wanted to call it that. That's horse 1. And then let's take a look at horse 2. Horse 2 is doing this, okay? From that standard position, from this horizontal, or from the other horse as our reference point, this is 60 degrees. And he's pulling at 250 pounds. Well, part of that is going in the same direction as the other horse, and part of it is pulling it off course. So we can say that the other horse is doing this, and this should look familiar. 250 pounds is the magnitude of the force, and then we'd multiply that by the cosine of 60 degrees. And then the vertical part, the part that he's pulling off course, is 250 times the sine of 60 degrees. Okay, so there's the other one. 250 cosine 60 degrees and 250 sine 60 degrees. Well, the resultant is going to be horse 1 plus horse 2. So we literally would just be able to add those together. But I want to draw a diagram of what's happening here. Here's horse 1. Okay, there's our 280 headed exactly in that direction. And kind of like the tail to tip method, if I put this one on here, this is what's happening. When that 250-pound horse pulls off in that direction, part of that is going in exactly the same direction as the 280-pound horse, and part of it is pulling it off course. And there, right there, that's our resultant. So that's geometrically what's going on. And let's see if we can see what happens when we add these together. So here's the resultant. I'm going to take the two horizontal components and add those together. 280 plus 250 cosine 60 degrees, comma, 0 plus that. So that would just be 250 sine 60 degrees. So there's the resultant. There we have it in component form. And if I want the magnitude of that, all I do is take each one of these components, square them, and take a square root. So this is going to be 280 plus 250 cosine 60 degrees, quantity squared, plus 250 sine 60 degrees, quantity squared. So let's throw that in the calculator and see what we end up with. Now, if we did this right, it better end up being the same answer. So let's see what we've got here. We're going to have a big square root, and then we've got 280 plus, let me start another set of parentheses here. So this is going to be parentheses, 280 plus 250 cosine 60 degrees, close the parentheses, and then we're going to square that. So I started again and closed it, and then we're squaring. And then we're going to add, start a set of parentheses, 250 sine 60 degrees, close the parentheses because that's that entire quantity. Then we're going to square it, and I'll close the parentheses so we can take the square root. So if we did this right, there we are right there. There's the 459.23. So the magnitude 459.23, and that's pounds. So we get that answer right. Now, we want to answer this question. What is this little angle right here? Well, the cool thing about this is our entire horizontal component here. There's the 280 plus the 250 cosine, okay? And this is the vertical component right there. So you'll remember, especially since this appears like it's in quadrant 1, we can at least get the reference angle by doing the tangent inverse of the vertical component over the horizontal component. So this is going to be 250 sine 60 degrees over, and I'd need to set a parentheses on this one, 280 plus 250 cosine 60 degrees. And let's have the calculator, figure out what that is for us. So I'm going to do tangent inverse, slide that down just a little bit, okay, and then the top is, I'll put that in parentheses, 250 sine 60 degrees. There's the entire top, divided by, let's put the entire bottom in there, 280 plus 250 cosine 60 degrees. Close the parentheses, hit enter, and there's our 28.1. Okay, so 28.1 degrees. So we did this problem twice. It might seem like this is more work, but again, it's very advantageous a lot of times to do things in component form, so keep that in mind. Really easy to draw a picture there, use the law of cosines. That might be a little bit comforting, but we want to keep that in mind. Okay, the next type of problem we're going to look at involves what we call an inclined plane. So an inclined plane. In other words, we're talking about a ramp. And so we want to think about this and consider the forces that occur when we put a mass or a weighted block or something like that on a ramp. Well, what happens is gravity pulls straight down. So I'm going to zoom in on this for just a second. Gravity pulls straight down on this. Okay. Now, I think in the book and in some other places, and maybe on your paper, we've got an arrow going this way, because normally we're interested in pushing up on the ramp. But I like to look at it this way. Makes a little bit more sense to me, and I think that's a little bit more typical. So if I put a weight on here, gravity pulls it straight down. So there's the force due to gravity right there. Well, what happens is with that gravitational force, when we put it on a ramp, it's broken up into two different components. One of them is perpendicular to the ramp, so perfectly perpendicular right there. Okay, and so this is called the normal force. Okay, and then we've got this other force that heads down this direction, kind of down toward the ramp. So we've got this other component, and that's kind of what's happening with the friction there. Friction is keeping that from sliding down there, so we could figure out how much friction would be there. This one's called the normal force. Not sure this has a particular name, but it does get broken into these two different components. And what happens when we make the ramp steeper, you'll notice that this green arrow stays exactly the same length, but the steeper it gets, the longer this blue arrow gets, and the shorter this normal force gets, and even steeper yet. Same gravitation here. This is going to be shorter and still perpendicular, and this becomes longer. And we could kind of get a little bit ridiculous with this. If we had the block straight up and down, there wouldn't be a normal force. We would just be heading straight in that direction. The gravitational force and the force due to gravity and that force that's wanting it to slide down there, they would coincide. So if you think about how hard we'd have to push on this block to make it go up, we'd have to push pretty hard. We'd have to push with a force equal to that force right there. Little bit more because it's a steeper ramp, little bit more because it's a steeper ramp, and we'd have to, in order to do this, we're really not pushing anymore. We'd have to pull with a force equal to or slightly greater than the weight of that block. So that's kind of the idea behind these problems, is how we'd break up this type of weight on a ramp. So in the textbook, there's a problem, and I'm not sure why they do this, but workers at a zoo, they've got to move a 250-pound giant tortoise to his new home. And they're going to drag this guy into a truck. Don't know why they put the rope around him, and it's kind of, that looks like he's going to do a face plant there or something. But that's the situation we've got here. So let's take a look here, and I'm going to zoom in on this one. Let's take a look at what's happening with these forces. He weighs 250 pounds, and gravitation is pulling that force straight down. We've got this ramp that's angled at 30 degrees, and they've drawn this line right here, this vector right here, to represent how hard they'd have to pull. Okay. Again, I'm going to switch that, and I'm going to have this going in this direction. We've got this normal force right here. So I'm going to take this, and I'm going to slide this over here. So I'm going to draw that in blue. Here's that normal force right there. So the two of these together, if you notice we've got tip to tail here, equal that result of 250 pounds coming straight down. Well, the question is, how hard do we have to pull on this in order to lead this guy up the ramp? So what we're trying to find is, what is the magnitude of this right here? We, of course, would just push directly along the ramp, so we'll assume we've got that part figured out. But we want to know what this one is right here. Well, you'll notice that I've got a big triangle right here. That one right there, that's a right triangle. This is a right angle, that's 30 degrees, so that's got to be 60 degrees up there. But I've also got a bunch of other right triangles. I've got this right triangle here, and I've also got that right triangle there. Well, if this angle right here is 30 degrees, and this one's coming straight down, this is a right triangle right here. This little tiny guy right here is a right triangle. That means this is 60 degrees. If that's 90 and that's 60, that's got to be 30 degrees right here. In other words, if we could kind of take this triangle right here and kind of flip that over, it would match up with this original triangle right here. That 30 degrees would line up right there. So let me draw this completely separately here. So here's what we've got. We've got a triangle that looks like this. This is the 250 pounds that come from that tortoise. This is a 90-degree angle right here. This is a 60-degree angle, and that is a 30-degree angle. And our question is, what is this right here? That's what we don't know. And that's all we need to find out here, is because they're asking for, find the force required to pull them up the ramp, or push them up the ramp if you wanted to think of it that way. So if I need this side and I've got that angle, and it's a right triangle, this is pretty easy. The sine of 30 degrees is going to be the opposite side, x, over the hypotenuse, 250. So x is equal to 250 times the sine of 30 degrees. And remember, the sine of 30 degrees is 1/2. So I end up with 125 pounds. So it's a lot easier than lifting him into the truck. But if we made that ramp even more shallow, we would hardly have to push him at all. So 125 pounds there. All right, let's take a look at the next type of problem. And these are some of the problems that are the most interesting applications. They're actually pretty cool. We're going to watch a video in just a second, but I'm going to zoom in on this right here. And let's talk about what happens when a plane is flying in the wind. So this vector right here, V1, represents the plane heading directly west. We've got this wind vector that's pushing kind of from the southwest to the northeast. So it's kind of pushing against its path. It's blowing it off course. You'll notice the plane is still pointed in that direction right there, but it's getting blown off course. So what we're interested in figuring out is, how fast is it actually going? Because the wind is definitely going to affect its ground speed. And what is this drift angle? How far has it been blown off course? So I'm going to show a quick video here. And I need to unmute this. And hopefully this picks it up just fine. If not, you can find this video on my website. So as you watch this, I want you to look at the airplanes here, and I want you to figure out which direction is the wind coming from, because they have to point into the wind in order to compensate for that wind. So I'm going to go ahead and hit play. So the runway's running here, and it's pointed off kind of to our left over here. So the wind would be coming from the left in that circumstance. This is kind of a cool one. This is a test of a Boeing 757. They set this up to land in crosswinds. It was pointed over here to our right, so the wind was coming from the right. Same thing here. You can see that this is pointed to our left, so the wind is coming from over here, and they're steering into the wind so they can run parallel with the runway and still land okay. Take a look at some of these other ones here. This is in Hamburg, Germany. This is a pretty interesting one. This is a 747 that's landing there. Which way is the wind coming from? Coming from over here on the left. They point into that, and then at the last minute they're able to correct their course, get the wheels on the ground, and then straighten out. Same airport here. I think this is in Lisbon, Portugal. Wind again coming from the left. Get that one on the ground safely. Same landing facility where Boeing tests. Wind was coming out of the right there. Okay, they kind of crab along, just kind of crawl sideways for a while, and then get the wheels on the ground and straighten it out. This is at the old Hong Kong airport. I think this is called Kai Tak. And this has 400 people or so on board, and look at the angle that comes in at. Look at that. Wind was coming from over here. Get the wheels on the ground, and I think if you watch really closely, that wing and engine actually touched. Here again is, I think in Portugal here. It would be really scary to be on that one. They had to do a go around. Here's that same airport in Germany. This is, I think this is a 767, and watch very closely. That wingtip actually touched the runway, did some damage there. They were able to get that to take off again. They did a go around. From what I understand, this was a co-pilot having their first shot at this type of landing, and luckily all ended well. But those are crosswind landings there. I'm going to mute that again. Let's come back and take a look at this. So what happens is, if they just continued pointing in that direction, they're going to get blown off course like that. So what they have to do is this airplane would actually have to kind of tilt off in this direction, pointing into the wind so that it continued heading in the direction that it wants to. So that's what we're after figuring out, and that's a pretty complicated problem. So we're going to take a look at a couple different ways to solve this problem. So here's the first situation, and I'll be honest with you, this one is, although it might seem really complicated, hopefully by the time we get done it makes sense. So we're going to solve this one using the law of cosines to start off with. But here's our situation. An airplane heads west at 350 miles per hour in a 50 mile per hour northwest wind. Okay, and when they say a northwest wind, they're telling us that's the direction that it's coming from. Find the drift angle, in other words, find out how much it's been blown off course, the ground speed, and the actual course of the airplane. And remember, when we're dealing with problems like this, we've got to keep straight that north in this system would be 0, south would be 180, this is 90 for east, and this is 270. But when we do the calculations, we're still working with our angles from standard positions. So this would be 0 and going that way. So when we're given measurements, we've got to make sure that we make that transition properly. Okay? So here's what we've got. We're going to use the law of cosines, and it says we can find the angle between the plane and the wind by subtraction. So let's think about this. We've got a plane that's heading west at 350 miles per hour. So that right there is 350 miles per hour. We've got a 50 mile per hour northwest wind. So the wind is coming from the northwest going to the southeast. So it's heading off in this direction right here, and that's 50 miles per hour. What we're after is what is the resultant, okay? It looks like a little bit of a headwind. It's blowing it off course and slowing it down just a little bit. So we want to know what's the resultant here, and we also want to know what's that angle there. Okay, well, let's think about this for just a second. If this right here is perfectly horizontal, and this right here is a northwest wind, well, this angle right here has got to be 45 degrees. Okay, so it's a perfectly northwest wind coming out of the northwest to the southeast. So we've got 45 degrees on that right there. So let me draw just a little bit larger picture of this. And here's what we've got. It's not much larger, draw it bigger than that. So this is 350, this is 50. We don't know what this is, but we do know that this is 45 right here. So you'll notice that what we've got here is we've got a law of cosines problem. So let's figure out what this one right here is. So the magnitude of that resultant is going to be a big square root of these two legs. So we'll do 350 squared plus 50 squared minus 2 times those two legs. So that's going to be 350, 50, and then the cosine of the angle between them. So the cosine here is going to be 45. So we're going to type that into the calculator and see what we end up with here. Clear that off. Big square root, 350 squared plus 50 squared, and then minus 2 times 350 times 50 times the cosine of 45, because that's the angle between those two. Okay, so we get 316. So it used to be going 350 miles per hour, but you can see some of that counted as a bit of a headwind. So we've got 316.62 miles per hour. Okay, that's the ground speed. Okay. And this problem has been set up to be relatively easy. Very seldom is something heading exactly due west. So this one does work out to be relatively easy. And then the next thing we need to find is we need to find this drift angle right here. So it's been blown off course. We want to figure out how much it's been blown off course. So if I know this right here is 316.62, well, I can then match these up because the sine of that angle right there, alpha, our drift angle, over 50, the side opposite, should be equal to, now I've got these corresponding guys right here. So this is going to be the sine of 45 over 316.62. Oops, not degrees. Okay, So if I solve this, I'm going to get alpha equals, I'll have to do the sine inverse. Sine inverse of, when I multiply over here, I get 50 on the top, sine of 45 degrees, and then 316.62, and I've still got that in my calculator. So let's figure out what alpha is. So here's our drift angle, and we're going to do, let's see, sine inverse. I'll do the top in parentheses, 50 sine 45, close the parentheses, and then we're going to divide that by 316. Oops. Well, I could type in 316, or I could just grab that last answer. So I'll delete that, and I'll put that last answer in there, close the parentheses, and see what we get. So alpha is 6.41, okay? Now, this right here, this is the drift angle. This is how much it's been blown off course. But it also asks for the actual course of the airplane. Well, if it was heading due west, that would be 270 degrees. That would be a bearing of 270 degrees. Well, let's see. Remember, north is 0, east is 90, this is 180. So we need to back off just a little bit. So our bearing, we'll say our course is, course bearing, let's call it. Course bearing is going to be 270 minus the 6.41. So we're going to end up with, and I'll just do subtract 270 here, change the sign, 263.58. 263.58 degrees. So if they were saying where they were headed, they'd be saying they'd be headed at 263. So not directly west, kind of a little bit west-southwest. Okay? So that's how to do that problem using the law of cosines. I'd like to show you, I'm going to stop the video when I'm done with this part and then break this up into two parts, but I'd like to show you how to do this problem using component form. And I find this to be easier for some reason. I'm not quite sure why. I think it's personal preference. Again, I'd advise you to try both methods. Try the law of cosines and try doing this in component form. So here's how we'll do this. Let's talk about the plane. The plane is heading due west at 350 miles per hour. Okay. Well, if we were to talk about putting that in component form, this is positive, this is negative, up is positive, down is negative, and so forth. All of this component is heading in the negative direction. So we could write that down as 350, 0, but we'd have to put a negative there because this is the origin and we're heading to the left. We could also do that. You'll remember we can take the magnitude of a vector and do the cosine of the direction. This would be 180 degrees. Okay? Again, don't get confused. Remember, we're talking about, these are the bearings, and then we still have to use our calculations using standard position being 0, heading off here to the right there. So that would be 180 degrees. So cosine 180, and then this would be the magnitude of the vector times the sine of 180. Well, the sine of 180 would be 0, that's why that's a 0, and the cosine of 180 would be -1, so that's why this is -350. So we've got the plane taken care of. All right, so let's talk about the wind. Well, the wind is heading off from the northwest to the southeast, like this, at 50 miles per hour. Well, since it's heading directly to the southeast, this angle right here would be 45 degrees for a reference angle, but we wouldn't want to use that. Remember, we'd want to use from standard position, so this would be 50, and this is going to be the cosine of 315 degrees, and then this is going to be 50 sine 315 degrees. So think about why that would be. Now, it's pretty easy to tell that this is going to be a negative vertical component and a positive horizontal component. So guess what 50 times the cosine of 315 is? Well, the cosine of 315 is radical 2 over 2, positive radical 2 over 2. So this is going to be 25 radical 2, or I'm just going to leave it as 50 cosine 315, comma, this is going to be 50 sine 315. Now, to be convincing and show that this actually does work, that this gives us the right answer, remember we said this is going to be 25, so if I multiply these, the 25, or the 50 cancels with the 2, so this is going to be 25 radical 2, And this one right here is going to be, well, this is down, so this is going to be negative radical 2 over 2. So this is going to be negative 25 radical 2. Okay? Now, let's just check and see and make sure that that actually works. Do we have the right thing? So I'm going to clear this off, and I'm going to do 50 cosine 40, whoops, not 45, 315. 315. Okay? For the heck of it, let's check out what 25 radical 2 is. There we go. And if I recall that, and all I'm going to need to do is just change this to a sign. So I'm going to change that to a sign. It's going to be the same number, and it's going to be negative. So I've got the right thing there. All right? So now, the resultant to this problem is going to be what I get when I add the plane and the wind together. So the resultant vector is going to be, and I'll write it with relatively simple numbers, negative 350 plus 25 radical 2, comma, this is just going to be negative 25 radical 2. Now, you can see that that's the case. Notice what happened here. Okay, let's go back up to this diagram. Remember, the wind was pushing against this, so it made the horizontal component shorter. It used to be 350, now it's a little bit shorter. You can see that subtraction taking place here. Negative 350, okay, and then we're adding 25 radical 2, and we were heading down, no doubt about that. That needs to be negative, okay? So the interesting part about this is, let's figure out what the magnitude is. It better match up with what we had before, but you remember we can just square each component. So this would be negative 350 plus 25 radical 2, comma squared. And this is going to be 25 radical 2, comma squared. Doesn't matter if it's negative there, but let's go ahead and get that, type that into our calculator, and see what we end up with. So this is going to be big square root, negative, whoops, let's start another set of parentheses, negative 350 plus 25 radical 2, square that, and then plus, start a set of parentheses, negative 25 radical 2, close the set of parentheses, square that, close them if we need to, and there's our 316.62 miles per hour. Okay? So even talking about this, you'll notice that this is, I mean, we look at the calculations that we had to compute here. This is relatively straightforward. Okay. The next thing we want to figure out is we want to figure out the drift angle. Okay. So let's talk about the drift angle. Now we know that we are here. We're back here because this is a big negative number and down. This is what we're looking at. So we're in quadrant 3. So in order to figure out what the angle is, remember, we're going to do the tangent inverse of the vertical component, negative 25 radical 2, over the horizontal component, negative 350, comma, whoops, negative 350 plus 25 radical 2. Okay, this is going to give us an angle, and it better give us that same angle that we got before. So I'm going to do tangent inverse. I'll put the top in parentheses, negative 25 radical 2. Close the parentheses, there's the entire top, divided by, start at the bottom, negative 350 plus 25 radical 2. Oops. Close the parentheses, hit enter, and there's our angle. Okay, our angle is 6.41 degrees. Okay, that's how much we're off course. Now we just need to go back to the original problem and think about, okay, well, wait a minute. I used component form to figure out the magnitude of the result of adding the plane and the wind, and I used the component form to figure out what this angle is right here. If that angle is 6.4, I still need to keep track, just like I did in the previous part, that I was heading in an angle at a direction of 270 degrees, and I'm going to subtract that. And what did we end up with before? I mean, it's the same angle, so 263.58. Okay, that's our bearing. Okay, all right. That is enough on this. You actually have enough information that you could do all the problems on the assignment. I am going to come back and I'm going to record another video where we look at some force situations like we had here, maybe an inclined plane problem, and definitely some more of these, because When something is heading either due west, due south, due east, it makes the problem very easy. So this problem was relatively simple compared to some of the ones you might see, but we'll come back and we'll take a look at these in a few minutes.